Okay, so we left our heroes here talking about weighted atomic averages, and now that you understand a little bit about what that atom is made of, and you can figure out masses, and you can do all that, and you can use the periodic table to find the mass and the number of protons, blah, 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 blah. Now, my friends, we are going to count atoms. Doesn't that sound exciting? Entrancing even? No? Not so much? Would you like to count the atoms in your desk? No? No, you would not? Understandable. Okay. This is the thing that moves from the realm of what seems reasonable to the realm of what seems preposterous, honestly. The idea that you could count atoms. Remember how tiny these things are? That we're measuring them? They're like 1,000th of a picometer. That's crazy. The idea that we could actually count them is pretty nuts. So the only reason we can count them, this is where my little critter friend comes in, is because of the mole. Who's my most likely victim here? Alec, heads up. Okay, that you're going to laugh at this. Woo! Good job, buddy. What is it? Hold it up. Hold up, my friend, for everybody to see. Aww, it's adorable. What is that thing? Okay. Nope.
I'm not a quarterback.
It's my little friend. It's a mole. They start to come out this time of year in anticipation of the big holiday next week. Aww. It's even fuzzy. It's got glue or something on its butt, though. Okay, so aside from star-nosed moles, those wonderful little mammals who tactily move their way through tunnels with their little feelers, there is a mole. Aside from the adorable little biology sense of the word mole, the mole is an SI unit. So the mole is the SI unit for the amount of a substance. This is just like a dozen. Okay? How many donuts are in a dozen donuts? 12. How many things are in a mole? 6.022 times 10 to the 23rd. 6.022 times 10 to the 23rd. It's just like a dozen donuts. That number of anything is a mole of that thing. Okay? It happens to be the amount of a substance that has the same number of individual particles as 12 grams of carbon-12. That connection will become important in a little bit. But it is the amount of a substance that contains 6.022 times 10 to the 23rd particles. Now, what are those particles? Typically here we're talking about atoms. As we move on into compounds, we will talk about formula units or molecules. But for right now, because we don't know about those things yet, we're just talking about atoms. 6.022 times 10 to the 23rd of anything is a mole of that thing. Just like 12 of anything is a dozen of that thing. Same idea. It is the amount of a substance. So 1 mole equals 6.022 times 10 to the 23rd of that thing, blank, whatever it is. Just like a dozen donuts is 12 donuts, a mole of donuts would be 6.022 times 10 to the 23rd. You'll notice that on that mole day assignments sheet, some of your math problems were things like if you had a mole of chocolate chip cookies and you ate 1 per second, how long would it take you to eat a mole of chocolate chip cookies? The answer will astound you. It's a lot of things. It's a lot of things. Okay? So let's now look at using it. Why does the mole matter? The mole matters because when we do what's called stoichiometry is fun to say, and we're going to start what's called compositional stoichiometry here, which is figuring out the ratios and numbers that make up compounds, just straight how much is in this thing. When we start to do reaction stoichiometry in Chapter 9, which is most people's far and away favorite chapter, we have to understand the unit of the mole because you're looking at individual atoms interacting with other individual atoms, and so you're looking at ratios. So we have to understand how to figure out how many moles of a substance we have in order to figure out how it will react with other substances. But that's a little bit down the road because then we're talking about compounds and we haven't gotten there yet. So that's why the mole is important, because if you can't figure out how many moles of something there is, you can never figure out how much of it's going to react down the road. Okay. before we get to how to use it, I guess I should point out that the number of particles in a mole, that 6.022 times 10 to the 23rd, do you get the sense that you're going to know this number by heart soon? You will. That number is called Avogadro's number after Emilio. Oh, he's got like 4 middle names because he was Italian nobility. Emilio something, 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 something Avogadro. He was, I think, I want to say an 18th century, again, rich white guys playing in the basement of the family castle. Scientist. He did work in chemistry of gases, and the number was named in honor of him. The idea that there was such a number was named in his honor because there were things he had proposed that hinted at this idea. He did not discover it. He did not propose it. He didn't even know this number. It was named in honor of him because his work had suggested that there would be such a number. So it's called Avogadro's number, hence my fun jokes about things like guacamole, made from mashed avogadros. Okay, molar mass. This is hugely important. This should have like big stars and fireworks and all sorts of things in whatever you're writing down, because this is going to be foundational for all the stoichiometry we're going to do. You know what atomic mass is, right? You look on the periodic table, you find the average atomic mass. For carbon, for instance, it's 12.01. For hydrogen, it's 1.0107. The molar mass is the mass of 1 mole of that substance. And in essence, it is the atomic mass given in grams. So the atomic mass of carbon is 12.011 AMUs because we're measuring atomic mass. The molar mass is 12.011 grams. The units matter significantly. The units matter significantly. So, you still got your periodic tables out from your quiz? Get them out. By all means, get them out. What is the molar mass of sodium? Forgot to hit resume. So the molar mass of sodium is 22.99 grams. The molar mass of anything is its atomic mass with the units changed to grams. So what's the molar mass of magnesium? Go. 24.30 grams, molar mass of magnesium. This is easy. This is easy. This is important because we're going to use molar mass as a conversion factor. Okay? We're going to start actually using the molar mass and using Avogadro's number to figure out how many particles are in a sample, to figure out how many moles are in a sample, or to figure out what the mass of a given number of particles is. So let's start that process. You got a GMA? You might not call her GMA, but I hope that somewhere in your life there is a GMA. I hope that there's a grandma somewhere in your life. So here is, yeah, actually my daughter doesn't call any of her female grandparents GMA. But it's a good mnemonic. Why is it a good mnemonic? I'm glad you asked. This will help you. This will guide you in conversions. Don't forget your GMA. You can't go wrong. Because you can go from grams to moles, aha, or moles to number of atoms. You can go from number of atoms to moles, and you can go from number of moles to grams. But you can't ever go straight from grams to atoms. Can't happen. Okay? So that's why we remember GMA. And I've had lots of people who write GMA on their tests so that they remember if they're going from grams to atoms, they have to go through moles first. It's a step-by-step conversion process. So we're going to start out, our first conversions that we're going to work with are going to be grams to moles. Okay? So this is a grams to moles conversion. And it's easy to just do this in terms of GMA. And we'll start with one-step conversions. All right, if I give you a sample, and that sample has 57.0 grams of, pick your favorite elements. Kobe, pick your favorite elements. Potassium. Hey, Kay, ha, Kobe, cool. Okay, so if you get 57 grams of potassium, that's K, and you want to know how many moles of potassium that is. This is just like the factor labels that we set up doing conversions. This is why the factor label system matters. Because you're now going from doing conversion, well, you're still doing conversions. Instead of doing metric conversions, you're now doing stoichiometrical conversions. This is stoichiometry. So what is true in any factor label setup? What has to match here to here? Okay, the chemical, what else? The units. Okay. So, down here we know that we have to have grams of potassium. This is just like doing the conversions for metrics. The units have to match so that it will cancel. Now, what do we want to end up in here? Moles. So we're going to put moles of potassium here. Yes, the abbreviation for moles is MOL. Mr. Voorhees often rails about this, and he says, well, that was really nice, so then they saved you one stinking letter. Yes, they saved you one stinking letter, but do not be tempted to write M or ML because those mean other things. So you can write out the whole word, or you can save, I guess, 2 letters, and, you know, instead of MOLES, you write MOL. But yeah, you need to write MOL. Yes, you have to write the chemical. Really? Seriously, Moser? I know what I'm dealing with here. Yeah, you do, right now. Right now, you're only dealing with one chemical. When we get into reaction stoichiometry, you're going to be dealing with multiple chemicals. So I want you to be in the habit now of always writing the units and the chemical. It will pay dividends later. I know it looks silly right now, but do it. Trust me. Because speaking as somebody who has screwed up stoichiometrical conversions because she didn't write her units, just telling you where the pitfalls are. Okay, remember that all conversions are based on a relationship where 2 things are equal. So if we go back to that idea of molar mass, 1 mole of a substance is equal to the atomic mass of that substance in grams. So you got your periodic table handy? All right. 1 mole of potassium is going to equal how many grams of potassium? Where are you going to get that number? What we are saying here is that this is equal to this. 1 mole of potassium equals 39.10 grams of potassium. So now it's just a factor label that we walk through. We're going to, if you want to see how this looks sort of metaphorically, 57 grams times 1 mole, all of potassium, divided by 39.10 grams of potassium. Move that over. So, grams of potassium cancels. What units are we left with? Moles of potassium. It's magic! And 57 times 1 divided by 39.10. Okay, so we get a raw answer. Remember that raw answer and sig figged answer. We get a raw answer of 1.4578005 moles of potassium. How many sig figs are we allowed to have? 3. This is multiplication and division. This is our given. You always base your sig figs on your given. Don't take your sig figs from conversion factors. So that 1 mole does not count against you. Okay? So you're going to base it on your given. Your given has 3 sig figs. That's what you're limited to. Your final answer will then be 1.46 moles of potassium. Okay, that's not too bad. We would like to know how many moles are in 21.5 grams of just oxygen, single oxygen atoms. So, do your setup. All right, do you have this? Is that what you got? Yeah, what's your raw number? What is it, Eddie? 1.34375. What are your units? Moles of oxygen. And our sig figged answer would be 1.34 moles of oxygen. We don't round anything. Okay, that's mole to gram to mole conversions. Those are pretty easy. Now, let's do another one-stepper. And that one-stepper is moles to atoms. Okay, so now we're going to do moles to atom conversions. Let me get rid of all these extraneous arrows. Okay, so I'm handing out the practice sheet, and with that you should be able to do the whole top part, which is all molar masses, and you should look for all the gram to mole conversions, because that's what we started with. We will pick up with mole to atom conversions tomorrow.